Hi everyone, welcome to the first part of a series on turbulence, wherein I attempt to teach myself turbulence and perhaps we could learn together. So, turbulence comes from the word turbulenza, which was coined by Leonardo da Vinci to describe these vorticities or vortical structures that he used to sketch. And just like all fluid flows can be described by Navier-Stokes equations, which were formulated by Navier and Stokes. In the early 19th century, the phenomenon of turbulence can also be understood to a great extent from these equations. However, if you know that for an equation to be well posed, we want to have a solution for it. So solutions should exist, and that solution should be unique. Also, we want that just because of small perturbations in the initial or the boundary conditions of the equations, there should only be very slight variations in the solution. Now, this means that, from a deterministic point of view, given the initial and the boundary conditions, the solution is known, but whether a solution is making the problem well posed or not is hard to see with respect to the third restriction. Now, there are certain solutions which are susceptible to large changes just because of small perturbations in their initial and boundary condition. And this is what leads to turbulence. So, Reynolds actually conducted an experiment in which he had injected a dye into a stream. And what he observed into a stream, which was basically flowing through a pipe with smooth walls. And what he observed was that when the flow was moving faster than the rate at which the dye was being injected into the stream, there was very little mixing as compared to the velocity of the flow. So this is laminar, right? And then gradually there was a transitional phase wherein the dye streak started to become wavy. And while at this point the flow is still laminar, you could see that there is a little mixing of dye with the water. Now, eventually, what happens is that there are erratic and quite significant mixing of the dye with the water. And this is what basically leads to turbulence. Now, turbulence has it's very hard to define turbulence. However, Chapman and Tobuck were able to describe the evolution for us to be able to understand it better. And what they said was basically that turbulence is defined by the Navier-Stokes equations, or to a large extent can be understood through the Navier-Stokes equations, and that the turbulence is chaotic, but it is not random, it is deterministic. The third is that turbulence is any chaotic solution to the 3D Navier-Stokes equations, which means that turbulence is three-dimensional, which means that one-dimensional and two-dimensional versions of the Navier-Stokes equations, which might have chaotic solutions, may or may not be turbulent. And then that these chaotic solutions occur as a result of successive perturbation of the laminar flow. So, because of some change in a parameter, which means that sensitivity to initial conditions is something which is very important, right? And that is what sets apart turbulent flows from highly irregular laminar flows. Now, since we have to a large extent an idea of what turbulence is, and From the streak and die example, if you recall, we know that when enhanced diffusion started happening, that's what we termed as turbulence. However, enhanced diffusion here is important, which is because it's not the same as the molecular diffusion. So if you recall the conservation of momentum equation, we have a nonlinear advective term on the left hand side, and then we have a diffusion term on the right hand side. And the diffusion term has viscosity in it, right? So at macroscopic scales, when viscosity is very small, then a nonlinear advective term dominates the flow. And when the viscosity is very large, the diffusion term dominates the flow. Now, when viscosity is very large, basically I'm talking about kinematic viscosity, the turbulence is not going to happen, right? Another thing is, which we discussed, was that it is very sensitive to initial conditions, which means that we should not be able to reproduce it or repeat it. So these are the few properties of turbulence, and probably in the next video we're going to discuss about the Navier-Stokes equations in a little more detail, and we'll talk about Boussinesq approximation and perhaps also some sort of some different types of turbulent flows. We would be talking about wall turbulence, wherein we'd be discussing the channel flow, and we'll also be talking about free turbulence, which occurs in free space, such as in a turbulent jet. So see you next time. Bye.